Would a container of 10 molecules of hydrogen or carbon dioxide have a larger volume? You might expect carbon dioxide might have a larger volume because the size of CO2 is much larger than a molecule of hydrogen. So if we had equal numbers of molecules, you might think, oh, the volume of this CO2 molecule is larger, so the molecules must take up more space, so we'd expect a larger volume. What we find, though, is neither one of these has a larger volume. They are equal. The reason why is because when we looked at the kinetic molecular theory, SMEC is how we remember it, the first one, S, stands for space, which says gases are mostly empty space. The size of the molecule is considered negligible. So it doesn't matter what the molecule is, whether it's hydrogen or oxygen, that size of the molecule is so small compared to all that empty space that they have equal volumes for equal numbers of molecules. Avogadro's law states equal volumes of different gases at the same temperature and pressure contain equal number of molecules, or we could also say moles. So these two tanks of gas, we have hydrogen and carbon dioxide. They both have 10 molecules in each of those containers. They have equal volumes, and the conditions are the same temperature and pressure in order to have the same number of molecules. And this is the same Avogadro from Avogadro's number, which is 6.02 times 10 to the 23rd atoms or molecules is equal to a mole. The formula for Avogadro's law is V1 over N1 is equal to V2 over N2. So V1 is my initial volume, N1 is my initial number of moles, and V2 is the final volume, and N2 is my final number of moles. So in this example below, down here, we have hydrogen, oxygen, and carbon dioxide gas. Each of these has 6 molecules within the balloons. So the balloons have the same exact volume because their moles are equal, their volumes must be equal. So again, it doesn't matter on the size of the molecule, so we can see carbon dioxide is much bigger than oxygen or hydrogen, but the volumes are equal because gases are mostly empty space. The size of those molecules, we're not really counting here. Avogadro's law relates volume and moles. As we said, equal volumes of gases at the same temperature and pressure contain the same number of molecules. We can also say the law follows that volume is directly proportional to quantity in moles, or using the formula V1 divided by N1 is equal to V2 over N2. In our picture down below, we can see the relationship between quantity and volume. We have 1 mole and 1 liter for our volume in the first example. If we add more molecules and we double the quantity, if we go from 1 mole up to 2 moles, the volume is going to increase. So our volume went from 1 liter to 2 liters. So this shows us the relationship between moles and volume. Increasing the number of moles will increase your volume. Based on Avogadro's law, your volume of your gas is proportional to the moles of the gas at the same temperature and pressure. So we can look at this child here. If he had an empty balloon, we add more gas to it when he blows into it, so we're increasing the number of moles, and then our flat balloon gets to a blown up balloon. And our relationship here is Avogadro's formula, V1 divided by N1 is equal to V2 over N2. So again, this formula will be given to you, as all your gas law formulas will be given to you, but you need to know the names that go along with the formulas and what the formula is about. So Avogadro relates volume and quantities. And as we stated earlier, equal volumes of gases contain equal number of molecules or moles. The chemical reaction for the formation of water is 2 moles of hydrogen plus 1 mole of oxygen produces 2 moles of water. Based on our coefficients, we know the number of moles of our reactants and our products. Avogadro's law tells us the quantity of moles is proportional to the volume. So in this picture below, we have hydrogen, and if we look at the volume of that and we compare the volume to oxygen, we have twice the amount of hydrogen than we do oxygen. The volume is 2 times as large. Water, we have 2 moles. The water is equal in volume to the hydrogen, whereas the oxygen volume is half the size. We can also look at the molecular level for hydrogen. We have 6 molecules. Oxygen, we have 3, so it's twice the number of molecules, gives us twice the volume. And water, when hydrogen and oxygen react, we form 6 water molecules. So they take up the same amount of volume as our hydrogen does, based on Avogadro's law. At constant temperature and pressure, a flat tire contains 1.0 moles of oxygen and has a volume of 0.10 liters. If 15 moles of oxygen are added to the tire, what is the volume of the tire? Let's start by writing down what's given. So our initial quantity, N1, is 1.0 moles. Our initial volume, V1, is equal to 0.10 liters. We're looking for N2, our new quantity. It says if 15 moles are added. Key word here is added. We started with 1 mole that was in the empty tire. That 1 mole didn't disappear. We just added 15 moles to it. So we end up with 16 moles for N2. The new volume, V2, is what we are looking for. So we are going to be using Avogadro's law because Avogadro's law relates the volume to the quantity in moles. So it's V1 over N1 is equal to V2 over N2. So when we looked at the first gas laws and we had Boyle's and Charles, Gay-Lussac's, and the combined gas law, those were all for a fixed quantity, which means N, or moles, was not involved in any of those calculations. So if I have a problem where we're discussing moles in the problem, Avogadro's law includes moles. So that's a hint here. You wouldn't use any of the other gas laws. So you always want to write down first your given information. Second is determine which gas law to use. So let's go ahead and solve this problem. So V1 is 0.10 liters. N1 is 1 mole. V2 is our unknown, and N2 is 16 moles. We want V2 by itself, so we multiply both sides by 16 moles. So we can cancel 16 moles on the right. On the left, we can cancel the moles. And now we just need to do the math. So we have 16 times 0.1 divided by 1 is equal to V2. And that's 1.6 liters. So that's our new volume. And that makes sense because we had a flat tire that only had 0.1 liters of air in it. Now we added more oxygen to it and our volume increased up to 1.6 liters. Standard temperature and pressure is abbreviated as STP. These are values that scientists assigned to temperature and pressure. Temperature units are Celsius, 0 degrees Celsius, or in Kelvin, 273 K. For pressure is defined at STP as 1.00 atm. These are values I do want you to remember. They will not be given. So no STP Temperature is 0 degrees C or 273 K, and pressure is 1 atmosphere. Molar volume is 1 mole of any ideal gas at STP has a volume of 22.4 liters. You do not have to remember that number. That's a number we can actually calculate. But we can look at down below here. We have helium, xenon, and methane gases. They're all at STP. So again, STP means pressure is 1 atm and temperature is 273 K or 0 degrees Celsius, and you can convert that to Kelvin. So they're all at STP conditions. Their quantities are all the same. They're all 1 mole. So if we have the same quantities, they're all going to have the same volumes. And it happens to be they all have a volume of 22.4 liters. It does not matter the size of the molecule. Again, methane is a much larger molecule than helium. The ideal gas law is PV is equal to nRT, where pressure is in atmospheres, volume is in liters, N is your number of moles of your gas, R is a gas constant, which is 0.0821 liters times atmospheres divided by moles divided by Kelvin. R value will be given to you when you're doing calculations. And temperature, your units are in Kelvin. So if you're going to use the ideal gas law, this is the second gas law that uses N, or number of moles. So Avogadro's does, but it's going to look at the relationship between a changing quantity of moles. Ideal gas law, the number of moles is not going to be changing. What volume does 1 mole of oxygen occupy at 0 degrees Celsius and 1 atm of pressure? First, we're going to write down what's given. So volume is our unknown. N is 1 mole. T is 0 degrees Celsius. And P is 1 atmosphere. So based on the information given to us, this is one that gives us N in moles, but the number of moles is not changing as it would be in Avogadro's. So this only option we can use here is the ideal gas law. The ideal gas law has R in it as well, which will be given to you. So it's 0.0821 liter atmospheres divided by mole. Okay. So the ideal gas law is PV equals nRT. We can solve for volume by dividing both sides by pressure, which is what's done here, and then plug our values in and solve for volume. Or I can just plug directly into PV equals nRT, which I'm going to do that below. So pressure is 1 atmosphere. Volume is my unknown. N is 1 mole. R is 0.0821 liter atmospheres divided by mole. Okay. And then my temperature is 0 degrees Celsius, which I need to add 273 to that. So my temperature is 273 K. And then I can go ahead and solve my problem by dividing both sides by 1 atmosphere in order to cancel those units. And then I get volume by itself. And on the right-hand side, I can cancel some units. So the moles will cancel, the ATMs cancel, the kelvins cancel, and I end up with liters. So then I can just do my math. I have 1 times 0.0821 times 273 divided by 1. When I do the math, I come up with 22.4 liters, which is what we saw on a previous slide. And I said you didn't have to memorize molar volume as 22.4 liters. We can calculate it. So again, that's if I have 1 mole of any gas, in this case oxygen gas, and it's at conditions of STP. STP means standard temperature and pressure. Temperature is 0 degrees Celsius, or 273 K, and pressure is 1 atmosphere. So at STP, your volume will be 22.4 liters. But again, you can calculate it. You don't have to remember that. So 1 mole of any gas at STP occupies 22.4 liters. So we can compare our 3 gases here. We have helium, oxygen, and nitrogen. If we have equal quantities, 1 mole, 1 mole, and 1 mole, they all have the same volume of 22.4 liters. And that's at conditions of STP, which are 273 K and 1 atm for pressure. The masses are going to be different because based on your periodic table, if you have 1 mole of a substance, they weigh different amounts. But again, the size of these molecules is minuscule compared to the amount of space in the gas that we don't need to worry about accounting for that. At what pressure would 2.5 moles of chlorine gas at 20 degrees Celsius occupy 20.5 liters? We're going to write down what's given. N is 2.50 moles. T is 20 degrees Celsius. We're going to add 273 to give us 293 Kelvin. And volume is 20.5 liters. We are looking for pressure. That is our unknown. And based on the information, we're given moles and only one quantity in moles, not changing any quantities. So we must use that ideal gas law. And in this case, we're looking for pressure. So we could divide both sides by volume and get this equation here and then plug everything in to get our pressure. Or we can just plug everything directly into the formula. So pressure times volume, which is 20.5 liters, is equal to N, which is 2.5 moles, times my R value, which is 0.0821 liter atmospheres over mole K, times temperature, 293 K. Now we're going to solve for pressure, so we need to divide both sides by 20.5 liters to cancel that out. So we end up with pressure by itself. And then let's cancel units on the right. We have a mole divided by a mole, a liter divided by a liter, a Kelvin divided by a Kelvin, and what's left are atmospheres, which is what we want for pressure. And then we just need to do our math. We have 2.5 times 0.0821 times 293 divided by 20.5. And I come up with 2.93 atmospheres for my pressure. A hyperbaric chamber has a volume of 200 liters. This is a photo of a hyperbaric chamber. This is used to treat scuba divers if they develop a condition called the bends. When scuba diving, you go below the surface. If you come back up to the surface of the water too quickly, you may need to go in a decompression chamber to get you back to equilibrium. So that's why you would use a decompression chamber. In this example, we want to know how many moles of oxygen are needed to fill the chamber at 300 degrees Kelvin to 3 atmosphere. And the second question will be how many grams. Let's start with question number 1 by writing down the information given. So we have a volume of 200.0 liters. N is our moles, which is our question, what we're looking for. And our temperature is 300.0 Kelvin. And our pressure is 3 atmospheres. Now, based on the information given, we're going to be using the ideal gas law because moles are given, but the quantity of moles are not changing. So we're going to use PV equals nRT. And our pressure is 3 atmospheres. Our volume is 200 liters. Our N is our unknown. R is 0.0821 liter atmospheres over mole. Okay. And our temperature is 300. Okay. In this problem, we want N by itself. So we're going to need to divide both sides by the same thing. So 0.0821 liter atmospheres over mole. Okay. And 300. Okay. That cancels everything on the right so that we'll get moles by itself. So we must do the same thing on the other side. So we have 0.0821 liter atmospheres over mole, okay, divided by 300K. So now we can look at our units, and we have an atmosphere canceling atmospheres, liters cancel liters, Kelvin cancel Kelvin, and this mole is on the bottom of the fraction, so that will be flipped up to the top as a mole. Then we can do our math. So we have 3 times 200 divided by 0.0821 divided by 300. And when I do my calculation, I come up with 24.4 moles is the quantity of oxygen that will be needed to fill the chamber. So that's question number 1. Question number 2 is how many grams? So this is review from a previous chapter where we need to convert from moles to grams. And to go from moles to grams, we use the molar mass. So we need the molar mass of oxygen. So we would go to our periodic table and we would see one oxygen is about 16, it's 15.99 grams per mole, but this is for O2, so it's our diatomic element, oxygen. So it's going to be 2 times that. So the molar mass is equal to 31.998 grams per mole. So now we can do our calculation. We have 24.4 moles of O2. 1 mole of O2 weighs 31.998 grams. Our moles of oxygen will cancel, and then we need to do the math. 24.4 times 31.998 gives me 780.75 grams. And I want to have 3 sig figs, so we'll change that to 781 grams of oxygen. That's our answer for the second part of the question. 24.4 moles for the first question.